Hello and welcome back. So in the last class we looked at the Carnot cycle, we also looked at heat engines and refrigerators. So we will look at some tutorial problems which involve the same. So the first one here says there's an engine which works on a Carnot cycle. We will remember that a Carnot engine or a Carnot refrigerator are both reversible. So this heat engine which works on Carnot cycle rejects 30% of the heat it absorbs from the source. So we are talking of a heat engine, an engine. So let's draw a heat engine here. So it takes heat from some high temperature reservoir, gives it to some low temperature reservoir, runs in a cycle. It rejects 30% of the heat that it absorbed from the source. So let's say this is QH. So what is given is that the low temperature heat which is rejected is 30% of what it absorbed. This is given. The sink is at 25 degrees centigrade. This is the sink. So this is the source and this is the sink, heat source and heat sink. It says the sink is at 25 degrees centigrade. So TL is what we are calling that. It's 25 degrees centigrade. Let's convert it into Kelvin. So it would very accurately be 298.15 Kelvin. We'll use 298 for the time being. That should be sufficient. We are asked to calculate the source temperature. So what we are asked to find out is the temperature of the source. So this is essentially what we are asked to find out. So what we know is that this works on a Carnot cycle. This is essentially a reversible engine. So we looked at the Carnot cycle. We said it has two reversible adiabatic processes, two reversible isothermal processes and so on. And what we also said is that if you have a reversible engine of this kind, then what we said is that the ratios of the heats transferred is equal to the ratios of the temperatures. We arrived at this by looking at a Carnot cycle between two temperatures and then looking at a sequence of Carnot cycles with intermediate temperatures, and then we said that this efficiency is a function of QL and QH, and then we said that it must be functions which cancel out if you multiply them. And we also discussed that Kelvin suggested that the function be the temperature itself, which is what you get if you use the temperatures in Kelvin. So we have this expression assuming that the temperatures are measured in Kelvin. Otherwise, of course, it will be the temperature in centigrade plus 273.15 divided by this temperature in centigrade plus 273 again. So we have this expression assuming that we are taking temperatures in the Kelvin scale. So we have QL by QH is essentially 0.3. That is TL, which is 298 divided by TH. Which gives us a value of 993.3 Kelvin. So that was essentially what we were asked to find out, the source temperature, and we have that. This problem doesn't ask for it, but what we can also do is find out the efficiency of this engine. So the efficiency is essentially the work done divided by the heat transferred. This is also doing some work. So the efficiency is work done, which is numerically QH minus QL, and the heat transferred initially, which is QH. So that's essentially 1 minus QL by QH. 1 minus this value is given, QL is 0.3 QH or QL by QH is 0.3. So, if this was a Carnot engine, it would have an efficiency of about 0.7. So, that is also something which we can find out. Let us go on to another problem. It says a heat engine operates between a hot reservoir at 500 Kelvin and a cold reservoir at 300 Kelvin. Okay, so there is a heat engine, it has a hot reservoir at 500 Kelvin and a cold reservoir at 300 Kelvin. Let us also draw this schematically. This is the engine. It takes in heat from the high temperature reservoir, gives it out to a low temperature reservoir and does work in the process. So, it absorbs 3500 joules. So, we will call this as QH, the amount of heat absorbed from the high temperature reservoir. So, that is given as 3500 joule. It rejects 2500 joules of heat. So, we have this as so we are asked to find out work done, efficiency and maximum possible efficiency. So, this is the information we have. We are asked to find out the work done, the efficiency and the maximum possible efficiency. So, if we apply first law for the engine, the first law for the engine which is in a cyclic process. So, the first law essentially says cyclic integral of del Q is cyclic integral of del W. If you are looking at an ordinary process, we also have plus du, but du for a cycle we know is 0, which is, so that gets cancelled out. So, we have this. So, or also we have sigma of del Q is equal to sigma of del W if you want to write it for discrete processes, or essentially if we integrate all of it, we have sigma Q is sigma W. So, the work done is sum of all the heat. So, essentially we have QH plus QL is equal to W, but what we know is that QH is coming in, so it is positive, QL is going out, so it is negative. So, the value of this will be minus something. So, I can take that sign into account already, and then keep in mind that I should not put a negative again because I have already taken the sign into account. So, this is what we have. So, the work done is essentially numerically QH minus QL. So, that is 3500 joules minus QL is 2500 joules. So, that is 1000 joules. The work done is positive for this engine because it is work done by the engine on the surroundings. We are asked to find out the efficiency. Efficiency is defined in all of these cases as what we want divided by what we have to give. So, the idea of a heat engine is it's a device which you can use to get work. So, what we are interested in is the work, and the question is what is the input to this engine? We are giving it heat at high temperature and it is rejecting heat at atmospheric temperature. So, what we are giving is essentially this QH. So, this is essentially the efficiency, but from the first law, from this expression, we also have this as QH minus QL by QH, or we can also write it as 1 minus QL by QH, which is what we were often doing. But in this case, we have already calculated the work. So, this expression is good enough. So, we have 1000 divided by QH is 3500. which comes out to be about 0.2857, which is 28.6%. So this engine takes in 3500 joules of energy, does 1000 joules of work, rejects 2500 joules of energy, and has an efficiency of about 29% or so. What we are also asked to find out is the maximum possible efficiency. So we know from Carnot's theorem that the maximum possible efficiency would be if this engine is a reversible engine. So maximum possible efficiency for an engine operating between these two reservoirs is the efficiency of a Carnot engine or a reversible engine. So we have the reservoirs at some temperatures. The temperatures were given as 500 Kelvin and 300 Kelvin. Our irreversible engine took 3500 joules, gave out 2500 joules and did work of 1000 joules. What would our reversible Carnot engine do? So the Carnot engine has an efficiency like all other engines of QH of essentially work by the input which we give. Work of the Carnot engine by QH given to the Carnot engine, different from the previous case, and we can write this from first law. W is the sum of all the sigma W is sigma Q. There is only one W. This is QH plus QL with the appropriate sign convention. QH coming in is positive, QL going out is negative. So this will be a positive value and plus a negative value. So I am taking that negative sign already here, or let me put a mod so I do not get confused later on. Let me also do that in the previous case. So I have already taken the negative sign out, so I should not put a negative sign again there. Similarly, in this formula, I have already taken out the negative sign. So whenever I am writing it as QH minus QL, it is actually sigma Q, which is all sum of all the heat transferred with the appropriate sign conventions. So wherever I put a negative sign in these kind of formulae, I have already taken out the sign, which is what is typically done in textbooks. So I am doing the same here. So I have this formula. So essentially this is 1 minus QL by QH. But we know that for a Carnot engine, QL by QH is essentially TL by TH if you take temperatures in the Kelvin scale. So the efficiency of the Carnot engine, which is the maximum possible efficiency you can get when operating between these two temperatures, is essentially 1 minus TL by TH. So I am substituting this into this expression. I get this. So this 1 minus TL is 300 Kelvin, TH is 500 Kelvin. So this is essentially what I get. So this is essentially 40%. So we see that if this engine was reversible and running on a Carnot cycle, it would have given an efficiency of 40% when operating between these two temperatures. We discussed earlier in the context of the Carnot cycle that the efficiency of a Carnot engine only depends on the temperature of the reservoirs. It does not depend on the substance or anything else. It is a reversible engine. It only depends on the temperature of the reservoirs, and it would have given an efficiency of this value. Depending on how much heat you supplied, it would have given different amounts of work and it rejected different amounts of heat, but the efficiency would have still remained the same. Now in contrast, when we have this real engine here, it gave us an efficiency of only about 28%. So we had a drop in efficiency from a possible 40 to the real value of 28, because we used an engine which is not reversible.